Hello friends, I hope you are doing well. IBM is my name and I want to take you to deformation of solids, that is part 2. Remember, we are solving multiple choice questions from past papers. Those of you who asked me to solve past papers individually, all the past papers have all been compiled into multiple choice questions per topic. I cannot solve all the past papers. I will only be solving the new past papers. The old ones have been compiled into topical past paper questions, which I have solved in paper 2. I've solved them in paper 4, and I'm currently solving multiple choice questions. So without wasting time, let's go to the document and start from where we stopped. I think we stopped on page 20 in part 1. So in part 2, let's start from page 21. An unstretched rubber cord is stretched by a force. The force F is plotted against the extension X. F is slowly increased from 0, causing the cord to extend along path P. F is then reduced back to 0 along path Q. What is represented by the shaded area? Remember, this is hysteresis. Rubber shows, or polymers show, a hysteresis behavior, where when the deforming force is removed, the material does not return to its original point, or it does not return to its original length following the same path. That is exactly how rubber behaves. Of course, it may remain elastic, but it does not return. It returns to its original path. Its original length, but following a different path. So, what is represented by the shaded area? The area below P with the x-axis. The total area below P with the x-axis shows the work done in loading. Then the area below Q with the x-axis, the area below Q with the x-axis shows the work done in unloading. So it means the area between P and Q will show the energy which is not returned, the energy which is wasted, or the energy which is dissipated as thermal energy. So our answer is going to be C. The energy dissipated as heat, that is the area represented between P and Q. A mass of 60 grams is suspended from a spring, and the distance from the bottom of the spring to the floor is measured to be 16.4 centimeters. The mass is replaced with 100 grams mass, and the distance from the bottom of the spring to the floor is now measured to be 12.6 centimeters. The spring obeys Hooke's law. What is the constant of the spring? So we know that if the spring obeys Hooke's law, the load is equal to the constant times the extension, which I'm going to call change in L. The load is given by the constant times the extension, so it means the extension K, the constant K, is going to be equal to the load. The load is changing from 60 to 100, so the load is going to be 100 minus 60, that is in grams. I'll first change it to kilograms, that is times 10 power negative 3. Then I change the mass to force, or to weight, which is going to be times 9.81. So this is going to be divided by change in L, which is from 16.4 to 12.6. 16.4 minus 12.6. Then I'll multiply this by 10 power negative 2 to change it to meters. So I'll check with my calculator. 100 minus 60, that is 40. Exponent negative 3. Then times 9.81. So that is the load. Divide by, I think 16.4 minus 12.6 is 3.8. So I will just say divide by 3.8. Exponent negative 2. And that gives me 10.3. So our value for K is going to be 10.3 newtons per meter. So the answer is going to be C. The graph shows the force extension graph for a wire. The wire is already extended by a force of 60 newtons. How much work is done to increase the extension of the wire by 2 millimeters? It is already extended by a force of 60 newtons. So let's check 60 newtons. Then we want to increase the extension by 2 millimeters. That means we shall increase this up to 100. So by 2 millimeters, that is 2 times 10 power negative 3. So it means the load is going to be 100. Okay, so we want how much work is done to increase the extension of the wire by 2 millimeters. So the work done is actually the energy stored, which is the elastic potential energy or the strain energy. So I'll use energy is equal to a half Fx or a half kx squared, but since it would involve calculating k again, I'll ignore k. So how much work is done to increase the extension? So the work done here is going to be, we shall start with a half times when the load is 100 times the extension, which will be 5 times 10 power negative 3 minus a half times 60 times 3 times 10 power negative 3. So we shall find the difference here. So a half is 0.5 times 100 times 5 exponent negative 3, then minus 0.5 times 60 times 3 exponent negative 3. So this is giving me 0.16. So this is 0.16 joules. So the answer is going to be C. The platform is suspended by 4 steel wires. There are 4 steel wires. Each wire is 5 meters long and has a diameter of 3 millimeters. The Young modulus of steel is 2.1 times 10 power 11 pascals. The wire obeys Hooke's law when a load of mass 200 kilograms is placed on the platform. How far will the platform descend because of the extension of the wires? How far will the platform descend because of the extension of the wires? Okay, so to begin with, we know that Young modulus E is equal to force, which is stress, or let me start with stress over strain, which will be stress is force over area, then strain divided by strain, which is extension of original length, so I'll get the reciprocal. So this will be original length over extension. Then they have mentioned the diameter, so I'll bring in diameter. So remember, area is pi d squared. Area is going to be pi d squared divided by 4. So this will be 4f times L naught divide by pi d squared, then times E. So that is going to be the expression for that is going to be the expression for Young modulus. So they told us the wires obey Hooke's law when the load of mass 200 kilograms is placed on the platform. So I'm just going to make the extension the subject. I'll make the extension the subject. So extension E total is going to be equal to 4 times the load, then times the original length of a wire, divided by pi times d squared, then times Young modulus. So we shall substitute here. So this is going to be 200. 4 times 200, that is the mass, times 9.81, that is changing the mass to weight, times the original length of each wire. They have told us that each wire is 5 millimeters, 5 meters long, but we don't know by how much it extends. So I'll just say times 5 times 5. Then I will divide this by pi. The diameter of each wire is 3 times 10 power negative 3, and this is squared. Then times the Young modulus, which is 2.1 times 10 power 11. So we shall check our calculator. So we have 4 times 200, then times 9.81 times 5, divide by, open brackets, we shall have pi times 3 exponent negative 3, which is squared, times 2.1 exponent 11. So this is giving us 6.6 times 10 power negative 6.6 times 10 power negative 3. 6.6 times 10 power negative 3. So that is going to be the extension. So this is going to be the actually this is what I've calculated here is extension of one wire if it was used alone, because there are 4 wires. So this is going to be the extension of one wire. So this would be the extension of one wire if it is used alone. 6.6, I'll add a 1 here, 6.61 times 10 power negative 3 meters. This is extension of one wire if it was used alone. But now there are 4 wires, and note that if the wires are used like this, they are behaving as if they're in parallel. If you recall how we handled the springs in parallel, if one extends by this, then if there are 4, it means total extension is going to be a quarter of the extension of just one. So this is going to be 1/4 times 6.61 times 10 power negative 3. It is going to be a quarter of 6 point, which gives us a 6.61 exponent negative 3 divided by, 6.61 exponent negative 3 divided by 4, which gives us a 1.65. So this is 1.6525 times 10 power negative 3, which is approximately 1.7 times 10 power negative 3 meters. Okay, so if I use 5 meters, if I use a diameter of 3 millimeters, and I use the Young modulus, whenever I'm using Young modulus, I'm looking at just one wire. Therefore, the extension I've got here would be the extension if the wire was used alone and the load of 200 was added. But now, since there are 4 wires, they will behave like they're in parallel. Therefore, the total extension is going to be a quarter of the extension of one wire. Why a quarter? Because there are 4 wires. So our answer is going to be C as opposed to D. D would be the extension if one wire is used for that load. A tensile force of 7 meganewtons is applied to a sample of steel. This causes the sample to extend by 5 millimeters in the direction of the force. The sample base Hooke's law. What is the work done to extend the sample? So work done is going to be equal to a half times Fx, which will be equal to a half times F, which is 7 times 10 power 6, because it is in mega, then times X. X is 5 times 10 power negative 3. So from my calculator, 0.5 times 7 exponent 6, then times 5 exponent negative 3. That is giving us 1 7500, which is 17.5 kilojoules. So that is 17,500 joules, which is 17.5 kilojoules. The force extension graph of a metal wire is shown. At which point on the graph does the metal wire stop obeying Hooke's law? Of course, Hooke's law is obeyed only where the straight line stops, so our answer is automatically A without wasting time. The diagram shows a large crane on a construction site lifting a cube-shaped load at a constant speed. This part is very important, at a constant speed. The material used for each part of the model is the same as that in the full-size crane, cable, and load. The model is 1/10th. The model is 1/10th full size in all linear dimensions. That means the stress, the strain is also going to be a 10th. The strain is going to be a 10th of the actual strain. So what is the ratio of stress in the cable on the full-size crane over stress in the cable on the model crane? So we know that Young modulus is going to be equal to stress over strain, and this is going to be equal to the Young modulus is going to be the stress. Then this is going to be times the dimensions we have. This is going to be, if I divide by strain, remember strain is extension over original length. So when I get the reciprocate, it will be original length over extension. But remember, they said the model is 1/10th full size in all linear dimensions. So that means this ratio here is going to be 1/10 because the model is 1/10th full size in all linear dimensions. So that means if I try to find the new Young modulus, the Young modulus is going to be stress times 1/10, which means if I want to obtain the stress, therefore the stress is going to be equal to 10 times E. So the question is, what is the stress, the ratio of stress in the cable on the full size crane over stress in the cable on the model crane? So if this is the full size, then for the model crane, it is just going to be E. So the ratio is simply going to be equal to stress in the full size crane, which is 10E. It means Young modulus in the model crane is going to simply be E. So that means our answer is going to be 10. So the answer is C. Note how I arrived at this. If I have the full size, the model crane, let it have dimensions where this is just going to be say 1. Then, and the full size, the model crane is a 10th, the full size is going to be just 1. So the stress on the full size crane will be 10 times that of the model. And that means our answer is going to be C. A horizontal metal bar PQ of length 5 centimeters is hinged at end P. The diagram shows the metal bar viewed from above. Two forces, 16 newtons and 5 newtons, are in the horizontal plane and act on end Q as shown in the diagram. What is the total moment about P due to the two forces? So first of all, I can resolve 16 vertically. I can resolve 16 in this direction. And when I use 30 degrees resolving 16, this will be 16 sine of 30. Therefore, this will have a perpendicular distance from P of 50 when I resolve it perpendicular. Therefore, they want us to take moments. So to find the resultant or the total moment about P. So this one is going to cause about P anti-clockwise. This one will cause clockwise. Therefore, I will have that 16 sine of 30 times the perpendicular distance, which is going to be 50. Then I will of course, 50 is in centimeters, so also times 10 power negative 2, then minus This force here is 5 times the perpendicular distance, which is 50 times 10 power negative 2, taking moments about point P. So when I check with my calculator, 16 sine 30, then times 50 exponent negative 2 minus 5 times 50 exponent negative 2. This is giving me a 1.5, so our answer is going to be A. So this is equal to 1.5 Newton meters, making the answer to be A. The diagram shows a wire of diameter D and length L that is firmly clamped at one end between two blocks of wood. A load is applied to the wire which extends its length by X. Okay. Second wire is made. The second wire is made of the same material, that means it is the same Young modulus, but of diameter twice D and length 3L. Both wires obey Hooke's law. What is the extension of the second wire? So I'm just going to equate the expressions of Young modulus for these wires. We know that Young modulus is going to be force over area times original length over extension, which is going to be equal to 4 times F over pi D squared, then times original length over extension. So since the wires are from the same material, the Young modulus is the same, so I will start with the first wire. Let the first wire, the same load is going to be added. Second wire is made of the same material, but that the wire obeys the second. What is the extension of the second wire when the same load is applied? So the load is the same, but the Young modulus will be the same because they are the same material. So I'll simply say 4 times the load. The original length of the first wire, let it be L, divide by pi, let the diameter of the first wire be D squared, then let its extension be E1. This should be equal to the second because the Young modulus is the same, that's why I'm equating 4F, but the length of the second wire is 3L, divide by pi, the diameter of the second wire is twice D, but this is squared, then let the extension of the second wire be E2. So using a different color, I will cross out some of these things. So 4F, L has cancelled, pi has cancelled. So I have 1 over D squared times E1 is equal to 3 over 4D squared times E2. So I wanted to show you that D squared also cancels. So it means if I make E2 the subject, E2 is going to be equal to 3 over 4 times E1. So, but they told us the load is applied to the wire which extends its length by X. So E1 is X. Therefore, this is 3 over 4 times X. Therefore, our answer is going to be B. Two wires, one made of brass and the other of steel, are stretched in an experiment. Both wires obey Hooke's law. That means they must be straight lines all through. Both wires obey Hooke's law, so A is wrong, C is wrong, because A and C are not straight lines throughout. The Young modulus for brass is less than the Young modulus for steel. The Young modulus for brass is less than the Young modulus for steel. Remember, Young modulus is equal to the gradient if we have a stress against strain graph. It is the gradient. So they are saying the Young modulus for brass is less than the Young modulus for steel, which means the gradient of brass should be less than the gradient of steel, which makes our answer to be B. Because brass is below, it means its gradient is less than that of steel for the same values of strain. An elastic material with Young modulus E is subject to a tensile stress S. Hooke's law is obeyed. What is the expression for the elastic energy stored per unit volume? Elastic energy stored per unit volume. So to begin with, we shall see that Okay, so to begin with, we know that Young modulus is going to be stress, which is given as S, over strain, but we don't have strain, but strain is extension of original length. When I get the reciprocal, it will be times original length over extension. If I make extension the subject here, it means extension is going to be equal to S, original length, over E. That is the expression for extension. But then, remember elastic potential energy is equal to a half times F times extension. The elastic potential energy is a half F times the extension. So I'll remove the extension. Also remember the force by Hooke's law. The force is equal to a constant times extension, or the force can be got from, remember stress is force over area. That means the force can be stress over cross-sectional area. The force can be stress over cross-sectional area. The stress is given as SA. So it means if I combine, potential energy is going to be a half times S times A, then times the extension. But this is going to be a half, the X times SA. Then where there is extension, I'm going to put this expression for extension. So it will be S L naught divided by E. Remember that A times L naught is going to be volume. So this one simplifies to a half. There's an E in the bottom. Then this is going to be S squared. Then times A times L naught. And A times L naught, that is volume. So E potential over volume is going to be S squared divided by 2E. So it means our answer is going to be C. I first established the expression for Young modulus from stress over strain, which is stress times original length over extension. I made the extension the subject, then the expression for potential energy, which is a half Fe, and I know F is stress times cross-sectional area. So I came up with this expression here when I substituted for F. Then when I brought in for E, I arrived at this point here. Remember, cross-sectional area times original length, that is volume. So the elastic potential energy per unit volume is going to be for that expression. Data for a steel wire on an electric jitter are listed. Diameter, Young modulus, tension. The wire snaps and contracts elastically, assuming the wire obeys Hooke's law. By what percentage does the length L of a piece of the wire contract? So we want strain as a percentage. So I'll just simply say that strain is equal to stress divided by Young modulus. So stress, remember stress is force over area. So I'll first, stress is force over area. So I'll say force is 20 over cross-sectional area, which is 5.0. No, they gave us diameter. So area is going to be pi d squared over 4. So the 4 will go up. So I'll say times 4 over pi. Diameter is 5 times 10 power negative 4, and this is squared. That is the stress. Then divide by this Young modulus. So I'll say times 1 over 2 times 10 power 11. So from our calculator, we have 20 times 4 divide by, open brackets, we have pi times 2 exponent 11. Okay, I'll first press my calculator there. Then I divide again by 5 exponent negative 4, but this is squared. So this is giving me 5.09 times 10 power negative 4. Now, as a percentage, I'll multiply this by 100 because strain is a ratio of extension over original length. So when I multiply this by 100 to change it to percentage, I think this gives me 5.09, which is 5.1 times 10 power negative 2%. So our answer is going to be D. The graph shows how the extension of a spring varies with the force used to stretch it. What is the strain energy in the spring when the extension is 4 centimeters? So when the extension is 4 centimeters, what is the strain energy? Of course, strain energy is going to be the area with the extension axis. So energy is going to be equal to a half. It will be a half times F times X, which is going to be a half, times F, which is 30,000, times X, which is 4 times 10 power negative 2. So we have a half, 0.5 times 30,000, then times 4 exponent negative 2, which is giving me 600. So this is 600 joules. So the answer is going to be C. Two wires X and Y are made from the same material. That means they have the same Young modulus. Wire Y has twice the diameter and experiences twice the tension of wire X. The wires obey Hooke's law and have the same origin length. Wire X has extension E. What is the extension of wire Y? So since they have the same Young modulus, I'll just equate the equations of both. Young modulus is going to be the force over area times original length over extension. Since they mentioned the diameter, area is going to be pi d squared over 4. So the expression will become 4f times the original length divided by a pi d squared times E. So for the first wire X, the Young modulus is going to be 4 times the tension T. Let its original length be L naught. Divide by pi, let the diameter has been given as D, so it will be D squared times the extension of wire T, wire X, which is E. This should be the same as for the second wire where the tension is twice T. So I'll say 4 into twice T. Then the original length, I think the length is the same. So times L naught. Divide by pi. The diameter of the second wire is twice D. So I'll put here 2D and I square. Let the extension of that second wire be EY. So some of these things will cancel out. 4T cancels out. L naught cancels. Pi cancels. So I am remaining with 1 over d squared times E equaling to 2 over 4 d squared times EY. So d has also cancelled. Remember, I want EY. So making EY the subject, we cross multiply. That will be equal to 1 over 2 times E. So our answer is going to be E over 2, which is B. What is represented by the gradient of a graph of force against extension? So force against extension, I think that is from Hooke's law, force is equal to K times X or K times extension. So it means if I compare with Y is equal to mx plus C. On the y-axis I have F, on the x-axis I have extension. So K the gradient is K, which is the spring constant. Forces are applied to the ends of a rod so that its length increases. The variation with the load L of the extension E of the rod is shown. The point P is the elastic limit. Which shaded area represents the work done during the plastic deformation of the rod? So plastic deformation must be after the elastic limit. So this one is not correct. And remember, work done must always be with the extension axis. So this one is not correct. I'm saying work done must be with the extension axis. So this one is, don't think about L as length. It is load. It is extension against load L. So the correct answer is going to be C. This one is not correct. After all, even the work done is with the load axis. This one is also not correct. The work done, because they gave us the total work done up to this point here, not the work done during the plastic deformation. Plastic deformation is this part here. So it means we need the area for this part here. This one was rejected because this area is with the load axis. It is supposed to be with the extension axis. Work done is always the area with the extension axis. So the answer is going to be C. A metal cylinder is able to withstand a compressive force of 4 kilonewtons without deforming plastically. If it can withstand 4 kilonewtons without extending plastically, it means the elastic limit. The elastic limit could be greater than 4 kilonewtons. Because if it can withstand 4 kilonewtons without deforming plastically, it means the elastic limit could be slightly greater than 4 kilonewtons. We know that stress is equal to force over area. So that means the force is going to be equal to the stress times the cross-sectional area. And this force here should be slightly greater than the force here, which is going to be exerting the force which is going to be exerted on this should be or can be slightly greater than 4 kilonewtons. So F could be greater than 4 kilonewtons because the cylinder has a cross-sectional area A and would be at its elastic limit. It would be at its elastic limit when a stress sigma is applied, and we have said the elastic limit could be slightly greater than 4 kilonewtons. So this could be F should be greater than 4 kilonewtons, or F should be slightly greater than 4,000 newtons. So we just look for a pair which will give us greater than 4,000 newtons. Let's check. The first one, 1.5 exponent negative 5 times 50 megapascals, 50 exponent 6. That is 1.5 exponent negative 5 times 50 exponent 6. So this is giving us 750. Let's check the second one. 1.5 exponent negative 5, then times 80 exponent 6. So this is giving us 1,200. So this is already out. Let's check the third one. 7.5 exponent negative 5, then times 50 exponent 6. So this is giving us 3,750. So this one will also be out. Then let's check this one. Oh, by the way, this was already out. So we have 7.5 exponent negative 5, then times 80 exponent 6. So this is giving us 6,000 newtons. So this means our answer is going to be D, because we said the force could be greater than 4,000 newtons. So our answer is going to be D. A wire has both elastic and plastic properties. When it is slowly loaded, its extension varies with the load as shown by the line OXY. The removal of the load is represented by line YZ. This creates areas P, Q, and R. P, Q, and R. Which area represents the maximum elastic potential energy stored in the wire? Of course, the maximum elastic potential energy will be that energy which can be now converted to other forms. Therefore, this one is showing the energy which cannot be regained. This one does not make any sense because it is going to be the area with the load axis. So this one here, this part here is going to show the maximum elastic potential energy stored in the wire. So the answer is going to be R. This one is the energy which is not returned. The area under OXY with the x-axis is the total energy, or Q plus R is the work done in loading the material. Then Z and Y, ZY, or the area under R, is the work done which can be converted into other forms. Therefore, that is going to be the elastic potential energy stored in the wire. So the answer is going to be D. In an experiment to measure the Young modulus of a metal wire, a wire is of the metal of the diameter 0.25 is clamped as shown. The wire passes from a clamp around a frictionless pulley and then to a second frictionless pulley where loads F are applied to it. A marker is attached to the wire so that the total length of the wire between the clamp and the marker is initially 3.7 meters. A scale is fixed near to this marker. The graph shows how the reading on the scale varies with F. So from here we can estimate, we are just going to take estimate. Let's assume this is in the center, but is slightly above the center. So instead of saying 4.5, I may say 4.6. And then this is 8. Okay. Then so it means the extension is going to be it's going to be 8 minus 4.6, which is approximately 3.4 millimeters. So I want to find the Young modulus, and we know that Young modulus is going to be equal to the force over cross-sectional area times original length over extension, which is going to be equal to 4 times, because they gave us diameter, so area is pi d squared. Area is pi d squared over 4, so the 4 goes up, so I have 4f L naught divided by pi times d squared times E. So I will substitute. That will be 4 times f. F is going to be 10 times original length. I think they gave us the original length at 3.7 divided by pi. Diameter was given as 0.25, so we shall say times 0.25 times 10 power negative 3 squared, then times the extension that we have found as 3.4 times 10 power negative 3. So I have 40 times 3.7 divided by, open brackets, we have pi, I'll open another bracket, 0.25 exponent negative 3, where this is squared, then and another bracket, 3.4 exponent negative 3. Then I'll close the outer bracket. So this is giving me 2.2 times 10 power 11. So this is 2.2 times 10 power 11 pascals. So the answer is going to be D. A scientist is investigating the properties of a new material. She plots a force extension graph for the material up to its breaking point. Which statement must be correct? Which statement must be correct? The area under the graph from P to R is the strain energy stored. That is not true. Strain energy would only stop at the point where we have elastic limit. The area under the graph from P to R is the work done in stretching the material. That would be correct. The total area under the graph from P to R is the total work done in stretching the material up to the breaking point. So that one is correct. Two wires X and Y are made of different metals. The Young modulus of wire X is twice that of wire Y. The diameter of wire X is half that of wire Y. The wires are extended with the same strain and obey Hooke's law. What is the ratio? Tension in wire X over tension in wire Y. So we know that Young modulus is equal to, I'll just put there 4F because we have done this several times, 4F over pi d squared, that is for the stress, then times original length over extension. So I'll just say times 1 over strain, because they said they have the same strain, and the strain is going to be, and Young modulus is stress over strain. Young modulus is stress over strain. So I'll just say times 1 over strain. So for the first wire, for the first wire X, they have told us the Young modulus of wire X is twice that of wire Y. So I will start with wire Y. Let its Young modulus be E. So this will be 4 times the tension in wire Y is going to be Ty divided by pi. The diameter of wire X is half the diameter of wire Y. So for let Y be D. So this will be D squared times 1 over strain. Then the other one, for the second one, the Young modulus is going to be, the Young modulus of wire X is twice that of wire Y. So I will say twice E is going to be equal to 4. The tension in wire X is going to be Tx divided by pi. The diameter of wire X is half. So I'll say times a half D squared. Then times 1 over epsilon because the strain is the same. So when I divide the two equations, I'm going to divide the two equations. So I'll set 2E divided by E is equal to 4Tx over pi, a quarter squared, 1 over 2 squared is going to be 1 over 4 D squared times epsilon. Then divide by, I will get the reciprocal. I will have pi D squared times epsilon divided by 4Ty. So I've divided this equation by this one here. I've divided this equation by this one. So using a different color, I will cross out some of these things. E has cancelled, pi has cancelled, D squared has cancelled, epsilon has cancelled, 4 has cancelled, and I'm remaining with a 2 on the left hand side. So 2 is equal to Tx. The 4 in the denominator here, 1 over 4, the 4 goes up. So it will be 4Tx divided by Ty. So Tx over Ty is therefore going to be 2 over 4. Tx over Ty is going to be 2 over 4, which is a half. So our answer here is going to be precisely B. A weight of 120 kilonewtons is placed on top of a metal column. The length of the column is compressed by 0.25 millimeters. The column obeys Hooke's law when compressed. How much energy is stored? So energy is going to be equal to a half times F times X. So this will be a half times 120,000, then times 0.25 times 10 power negative 3. So I'll just press my calculator. A half times 120,000 times 0.25 exponent negative 3. So this is giving me 15. So this is 15 joules, not kilojoules, it is 15 joules. A wire of diameter D and length L hangs vertically from a fixed point. The wire is extended by hanging a mass M on its end. The Young modulus of the wire is E. The acceleration of free fall is G. Which equation is used to determine the extension? So we know that Young modulus is equal to force over area, which is the stress, then times original length over extension, which is the reciprocal of the strain. Since they have mentioned diameter, so this becomes 4F over pi D squared times original length over extension, which is going to be, at find force, it will be mg, so this will be capital M times G times L divided by pi D squared times the extension E, making E the subject, so E will be equal to 4 M GL divided by pi D squared times the Young modulus. So our answer is going to be D. The variation of the compression of a spring with the force applied to it is shown in the graph. A block slides along a horizontal frictionless surface towards the spring as shown. The block is brought to rest by the spring when the spring reaches a compression of 4 centimeters. So we can check 4 centimeters. 4 centimeters corresponds to a load of 8 newtons. All the kinetic energy of the block is transferred to elastic potential energy. What is the kinetic energy of the block when it first makes contact with the spring? So the kinetic energy, because all the kinetic energy becomes the elastic potential energy, so this is going to simply be equal to a half Fx. So this would be a half times F. F corresponds to 4 centimeters, we have seen it is 80 newtons. Then times extension, which is 4 times 10 power negative 2. So a half is 0.5 times 8 times 4 exponent negative 2, which gives us 0.16. So this is going to be 0.16 joules. So the answer is going to be A. The diagram shows 2 points P and Q which lie 90 degrees apart on a circle of radius r. A positive point charge at the center of the circle creates an electric field of magnitude E at both P and Q. Which expression gives the work done in moving a unit positive charge from P to Q? Of course, this question is in electric fields, but it is out of this syllabus, but I would still answer it. We know that work done in an electric field is the charge times difference in potential. For a point charge, because a positive point charge there's a positive point charge at the center, so it is creating a field around it. For a point charge, we know that the potential at a given point from that charge is equal to the charge divided by 4 pi epsilon naught r. So it means the potential at Q will depend on the radius. Potential at P will also depend on the radius. And these two charges are identical. These two charges are going to be identical. And even if they are not identical, the diagram shows 2 point charges P and Q, which lie that a positive point charge at the center of the circle creates an electric field of magnitude E. So the potential at these 2 points is determined by the charge at the center, which I'm calling capital Q. The work done is smaller q times difference in potential. Because the radius or the distance from point P to the center is the same, it means that there is no difference in potential. So when I move from Q to P or P to Q, the difference in potential is 0. And since work done is the small charge placed at that point times the difference in potential, it means the work done is going to be 0. So our answer would be A. But I say this question is out of the syllabus. This question is in the new, this would be appearing in paper 4 rather than paper 2 or paper 1. A cable on a suspension bridge supports a weight of 19.3 times 10 power 5 newtons. This weight causes the cable to stretch by 47 millimeters. A lorry crossing the bridge then increases the force on the cable to 23.3 times 10 power 5 newtons. The extension graph for the cable is shown. The extension graph for the cable is shown. What is the increase in strain energy in the cable when the lorry is crossing the bridge? So the increase in strain energy is going to simply be this area here. And if we can take it to be a trapezium if you want. It is going to be the trapezium. So the increase in energy, I'll call delta EP, is going to be, remember, energy is going to be, I'm taking the area of this, which is a trapezium. So the energy is going to be equal to the area under that part. So this is going to be a half, taking it as a trapezium. This could be A, that could be B, this could be the height. So this would be 19.3 times 10 power 5 plus 23.3 times 10 power 5. Then times this difference is 57 minus 47, which is 10. So I'll say times 10 times 10 power negative 3. Remember, area of a trapezium is a half into A plus B times height. But of course, this formula is not necessary. Here, you just notice you are finding the area of a trapezium. So this is going to be equal to a half, which is 0.5 times 10 exponent negative 3, then times, I'll open two brackets, 19.3 exponent 5 plus 23.3 exponent 5 and close the brackets. So this is giving me 21,300, which is the same as 21 kilojoules. So it can be 21 kilojoules. So our answer can be A. What are the units of stress, strain, and Young modulus? For strain, there is no unit. So this one is wrong, that one is wrong. For Young modulus, it can be pascals. For stress, it can also be pascals. So the answer is going to be D. Stress is pascals, strain no units, Young modulus pascals. A rubber band is stretched and then relaxed to its original length. The diagram shows the force extension graph for this process. As the force is increased, the curve follows the path OPQ to the extension E. As the force is reduced, the curve follows the path QRO to return to zero extension. That means the material is elastic, only that it follows a different path. The area labeled X is between the curves OPQ and Q and QRO. The area labeled Y is bounded by the curve QRO and the horizontal axis. Which statement about the process is correct? So let's inspect this. Of course, we know that this area here is the area the energy which is dissipated as thermal energy. The area under the curve OPQ with the x-axis is the total work done in loading. The area under ORQ and the x-axis is the work done in unloading. So area X is the energy which hits the band. Let's see. Area X is the energy which hits the band as it is stretched to extension E. Area X is the energy which hits the band as it is stretched to extension E. The area X is the energy which hits the band as it is being stretched. There is no this is not going to be correct because although area X is the energy which is dissipated or which is not returned, the energy which is not returned during unloading, then area X plus area Y is the minimum energy required to stretch the band to extension E. Area X plus area Y, that is very true. The total area under the graph here with the x-axis is area X plus area Y. That's the work done in the loading. So the answer is going to be B. Two wires with the same Young modulus E and cross-section area A but different lengths L are subject to different tensile forces. Remember, they have the same Young modulus. The extension E of each wire is the same. The column headings in the table show four different quantities. Which quantities have the same value and which quantities have different values for the two wires? Okay. First of all, before we inspect the table, we know that Young modulus is going to be force origin length over cross-sectional area times E. I will put a star on those which are constant, which are the same for both wires. Two wires with the same Young modulus E, so this is a constant, and the cross-sectional area A, this is a constant, but different lengths. L are subject to different tensile forces, F. So F and L are different. The extension E of each Y is the same, so this one is also constant. So first of all, I can say that FL can be equal to E times A times E. The extension E of each wire is the same. Which quantities have the same value and which quantities have different values for the two wires? The first one is FL over E. FL over E, if I make FL over E the subject, FL over E is going to be E times A, where E times A is a constant, so that means these ones will have the same value. So FL over E should be the same, so that one is eliminated. Let's check AE over L if it is also a constant. AE over L, when I make AE over L the subject, AE over L the subject, this is going to be equal to F over Young modulus. AE over L of the subject is F over Young modulus. Remember, F is not the same. Although Young modulus is the same, F is not constant, so that means AE over L is not a constant, so this is going to be different. This one is going to be different, so we have to choose about from those two. Then E over FL. Let's make E over FL the subject from this equation. E over FL the subject is going to be equal to 1 over AE. And 1 over AE, since the area is the same and E is the same, it means 1 over AE is going to be the same. Therefore, E over FL will be the same. So the answer is going to be D. Note how I arrived at this. This was constant, it was the same. So FL over E will be the same. Then I'm saying E over FL is equal to 1 over AE. And since area is the same and extension is the same, 1 over AE is the same for both wires, which means E over FL is the same. That's why the answer was D. Okay. Two springs X and Y stretch elastically. The graphs show the variation with the extension X of the force F applied to each spring. Which statement is correct? Okay, we can first of all check the constants. K here is going to be 20 over 10. I'm not changing the units, so it will be 2 newtons per centimeter. And here it will be K is going to be equal to 80 over 5, which will be 8 over 5. 80 divided by 5, which will be 16 newtons per centimeter. When each spring is given the same extension, energy stored in Y is 4 times the energy stored in X. Let's inspect that. We know that energy is going to be equal to a half kx squared. X is going to be the same. So the ratio is going to be equal to, they said energies, when the spring is given the same extension, the energy stored in Y is 4 times the energy stored in X. So let's find energy in Y over energy in X. So this is going to be a half. K in Y is going to be 16 times X squared, because X is going to be the same, divided by a half. K in X is 2, then times X squared. So we see that this one gives us 8. So this is going to be 8. The ratio is 8. So it means energy in Y over energy in X is 8. So energy in Y is 8 times energy in X. When each spring is given the same extension, that is when X is the same, the energy stored in Y is 8 times the energy stored in X. So the answer is going to be B. The diagram shows the force extension graph for a steel wire up to its breaking point. What is the best estimate? What is the best estimate of the work done? The work done to break the wire. So the work done is going to be the area under this graph. I don't think it is a trapezium. Okay, so I'm going to find the area under this graph. So the energy or the work done is going to be, I'll first find the area of the rectangle here. Remember, this is going to be 1. So 1 to 10, that is 9. Then 200, so I'll say 200 times 9 times 10 power negative 3. That's the area of this rectangle. Then plus, I'll add the area of this triangle here, which is going to be a half, times the base, which is also 9, times 10 power negative 3. Then times the difference between 200 and 250 is 50. Then plus, I'll add the area of this triangle here, which is a half. The base is going to be 1 times 10 power negative 3. Then times the height, which is 200. So let's find the total there. So I have 0.5 times 200 times 9 exponent negative 3. No. The first area is 200 times 9 exponent negative 3 plus the second area is 0.5 times 50 times 9 exponent negative 3 plus the third area is 0.5 times 200 times 1 exponent negative 3. So this is giving me a 2.125 joules. So the answer is going to be A. A spring is loaded with weights. When the weights are removed, the spring returns to its original length. The spring is then loaded with heavier weights. When the weights are removed, the spring is longer than its original length. So this one is plastic deformation. Which types of deformation are shown by this experiment? The first one is elastic, the second one is plastic. So both elastic and plastic deformation. So the answer is A. Both elastic and plastic deformation. The stress-strain graph for a metal is shown. What is the strain energy per unit volume of a rod made from this metal when the strain of the rod is 0.1? So when the strain is 0.1, the stress is going to be 2. And remember, the area under this graph, we have seen it is the same as the elastic potential energy or the strain energy per unit volume. For a stress-strain graph, we have showed that the area is equal to the elastic potential energy per unit volume. And this is going to be equal to a half times 0.01, then times 2 times 10 power 9. So this is going to give us 0.5 times 0.01 times 2 exponent 9, which gives us these are 3, these are 6. So that is 10 mega. This is 10 times 10 power 6 joules, which is 10 mega joules per meter cubed. So the answer is D. If you cannot recall how the area is equal to the elastic potential energy per unit volume, I can show you here. Area is going to be equal to stress. It is going to be a half of the stress times the strain. This is going to be a half. The stress is force over cross-sectional area, and the strain is going to be extension over original length. So this is going to be a half times Fe, then times 1 over area times original length. This is strain. This is elastic potential energy or strain energy, a half Fe, and this one is volume. Cross-section area times original length, that is volume. So this gives us elastic potential energy per unit volume. A bolt is subjected to a tensile. So here I said the answer is D. A bolt is subjected to a tensile force as shown in the figure. The bolt has a circular cross-section. At end X, the diameter is twice D. At end Y, the diameter is D. What is the ratio? Stress over strain. I mean stress at y versus stress at x. So we know that stress is equal to force over cross-sectional area, which becomes 4F over pi d squared. So stress at y is going to be 4, because the tensile force is the same, so it is going to be 4F over pi. The diameter is d squared. Divide by stress at x, so I'll just get the reciprocal. So times stress at x, I'm getting the reciprocal, which will be pi. The diameter at x is twice d, but this is squared. Then divide by 4 times f, because the tensile force is the same. So 4f has cancelled, pi has cancelled, so we remain with the ratio, which is 4 d squared divided by d squared, and this gives us a ratio of 4. Note that here I have divided the two equations for this part and this part. This equation is for this part here, and the other equation was for the other part there. So I divided the two, that's why I got the reciprocal. When I get the reciprocal, then I get the ratio as 4, so the answer is going to be D. A rectangular block of steel supporting a very large component of a bridge has a height of 15 centimeters and a cross-section of 2 by 12 centimeters. That is giving us the area. It is designed to compress 1 millimeter when under maximum evenly distributed load. The Young modulus is that. What is the maximum load it can support? So we know that Young modulus is going to be equal to the load F over cross-sectional area, then times original length over extension. So I want to find F. So F is going to be equal to Young modulus, then times cross-sectional area, then times extension over original length. So this is going to be, the Young modulus is 2 times 10 power 11 times the cross-sectional area. This is going to be over 100 over 100. So the cross-sectional area is going to be 0.2 times 0.12. That is the cross-sectional area when I convert to SI units. Then times the extension, which is going to be 1 times 10 power negative 3. Then divide this by, it is 1 times 10 power negative 3. Then divide this by the original length, which is going to be 15 times 10 power negative 2, because a rectangular block of steel supporting a very large component of a bridge has a height of 15 centimeters. So I'll just press my calculator. So I have 2 exponent 11 times open bracket 0.2 times 0.12, then times 1 exponent negative 3 divided by 15 exponent negative 2. So this is giving me 32 millions. So this is 32 millions, which is 32 mega newtons. So the answer is going to be A. A sample of metal is subject to a force which increases to a maximum value and then decreases back to 0. A force extension graph for the sample is shown. When the sample contracts, it follows the same force extension curve as when it was being stretched. What is the behavior of the metal between X and Y? Between X and Y. But they said it follows the same force extension curve as when it is being stretched. So that is when it contracts. Therefore, this cannot be considered to be a plastic region. It cannot be considered to be a plastic region because it goes back. It goes back to 0. It means there is no extension retained. So we can't talk about plastic. Where I see plastic, both elastic and plastic, no, not elastic. It is elastic. Plastic but not elastic. That's not true. It is elastic but not plastic. It is elastic because it returns to its original length, only that when the sample contracts, it follows the same force extension curve as when it was being stretched. And here they said, and then decreases back to zero. So it means it is elastic but not plastic if it goes back to zero. A load is hung from the end of a metal wire. The load is increased and the wire stretches elastically. The table shows the length of the wire for different loads. When the load is 4 kilonewtons, what is the strain energy stored in the wire? So we know energy is going to be equal to a half Fx. That is the strain energy. So this will be a half. The load is 4 kilonewtons, that is 4,000. Then x. X will be 408 minus 500 because when there is no load, the length is 500. So the extension is going to be 508 minus 500, which is 8 millimeters. So it is 8 times 10 power negative 3. So 0.5 times 4,000 times 8 exponent negative 3. That gives us 16. So this is 16 joules. So the answer is going to be A. A metal wire is stretched by a load. The force extension graph is shown. What is represented by the area under the hollow graph? That is the work done in stretching the material until it breaks. So the change in gravitational potential energy, not the energy that would be released from the wire if the final load was removed. That's not true. The energy transferred into heat energy. That's not true. The work done in stretching the wire. So the answer is going to be D. The Young modulus of steel is twice that of copper. A 50 centimeter length of copper wire of diameter 2 millimeters is joined to a 50 centimeter length of steel wire of diameter 1 millimeter, making a combination wire of length 1.0 meters as shown. The combination wire is stretched by a weight added to its end. Both the copper and the steel wires obey Hooke's law. What is the ratio extension of steel over extension of copper? Okay, let's come back here. So we know that Young modulus is equal to force over area, that is stress, then times original length over extension, which is the reciprocal of the strain. They gave us diameter, so we shall include diameter, so it becomes 4 times the load, 4 times the load, which is F, divided by pi d squared times original length over extension. So I will start with the copper. Extension for copper is going to be equal to 4F times original length divided by pi d squared divided by pi. Okay, let me just substitute, making it the subject. Extension for copper, extension is going to be equal to 4F L naught over pi d squared times Young modulus. So let me say extension for copper. I'm just going to put the values. The load is the same, so I'll say 4 times F. Original length for copper, the length is the same, so I'll just say L naught divided by pi. Diameter of copper is 2 millimeters, so I'll not change the units, I'll just say 2 but squared. Then Young modulus of copper, the Young modulus of steel is twice that of copper, so let that for copper be E. Then extension for steel is going to be equal to 4F times original length, which is L naught over pi. The diameter of steel is 1 millimeter, so I'll just put 1 squared times. The Young modulus of steel is twice that of copper, so that is twice E. So we want ratio steel over copper, so I'm dividing the two equations. Ratio extension over steel over extension of copper is going to be, when I divide, I will get the reciprocal. So I'll say 4F L naught over pi, the one is useless, even if I square, times 2E. Then I get the reciprocal, which will be pi times 4E divided by 4F L naught. So the denominator here has cancelled with that one. Pi has cancelled, E has cancelled. So this is 4/2, which is going to be 2. So the ratio is going to be 2. So the answer is going to be B. A sample of metal is stretched by a tensile force to a point beyond its elastic limit. The tensile force is then reduced to 0. The graph of force against extension is shown below. Which area represents the net work done on the sample? Net work done on the sample. So a sample of material is stretched by a tensile force to a point beyond its elastic limit. Tensile force is then reduced to 0. The graph of force against extension is shown below. Which area represents the net work done on the sample? So the net work done on the sample is going to be the area under this part plus the area under that part there. Therefore, our answer is going to be X plus Y, the net work done on the sample. A spring balance consists of a spring of length 20 centimeters with a hook attached. When a fish of mass 3 kilograms is suspended from the hook, the new length of the spring is 27 centimeters. What is the spring constant? K. So we know that K is going to be equal to the load divided by the extension X. The load is going to be 3 times 9.81. The extension is going to be 27 minus 20, which is going to be 7 times 10 power negative 2. So 3 times 9.81 divided by 7 exponent negative 2. So that gives us 420 newtons. So this is 420 newtons per meter. So our answer is going to be D. A metal wire is attached at one end to a fixed point and the load is hung from the other end so that the wire hangs vertically. The load is increased from 0 to 20 newtons. This causes the wire to extend elastically by 5 millimeters. The load is then reduced to 12 newtons and the extension decreases to 3 millimeters. How much strain energy is released during the unloading process? During the unloading process. So energy is going to be equal to, so we want this area here. So energy is going to be equal to a half. I'm going to consider this as a trapezium. So this is going to be 12. That is a half into A plus B times height, area of a trapezium. So let A be 12, B will be 20. Then the height is going to be this one, which is 5 minus 3, which is 2 times 10 power negative 3. So 0.5 times 12 plus 20, then times 2 exponent negative 3, which gives us 0.032, which is going to be D. That is 3.2 times 10 power negative 2 joules. The diagram shows the force extension graph for a sample of material. The sample is stretched and then returns to its original length. Which area represents the work done to stretch the sample? Of course, it is going to be the total area under the graph, work done to stretch the sample, which is going to be Q plus R. So the answer is going to be C. A metal wire of cross-sectional area 0.2 millimeters squared hangs vertically from a fixed point. A load of 84 newtons is then attached to the lower end of the wire. The wire obeys Hooke's law and increases in length by 0.3%. That means the strain is going to be this. What is the Young modulus of the metal wire? So Young modulus is equal to stress, which is force over area, times 1 over the strain, times 1 over the strain. So they have told us the increase in length is 0.3%. That means the strain is going to be 0.003, I think. 0.3 divided by 100, 0. I think that is 0.003. That is the strain. So this is going to be the force, which is 84 divided by the area. I'll change the area from millimeters squared to meters squared. So that is 0.2 times 10 power negative 6. Then in the denominator, I'll just say times 0.003. So this is going to be 84 divided by 0.003 times 0.2 exponent negative 6. So this is giving me 1.4 times 10 power 11. So this is 1.4 times 10 power 11. Note that this one, the increase in length, is like extension over original length. Then when I multiply it by 100, is the increase in length as a percentage, which is the strain. So the answer is going to be D. The diagram shows a beam supported on two pivots. Which statement describes the state of the top? Of course, in the top we have this is going to be a compression. At the bottom it is a tension. So both X and Y are in compression. That's not true. Both X and Y are in tension. That's not true. X is in compression, which is very true, and Y is in tension, which is very true. So at the bottom, the parts are, it's like they are pulled apart. At the top, it is like the parts are coming together. So X is in compression and Y is in tension. A copper wire hangs vertically from a fixed point. A load is attached to the lower end of the wire, producing an extension X. The wire obeys Hooke's law. Which single change gives an extension of 2x? So we know that Young modulus is going to be equal to, because it's going to be a constant, is going to be force over cross-sectional area times original length over extension. So if the extension has been doubled, to maintain the same Young modulus, F is equal to E is equal to F over, if extension has been doubled, to maintain the same Young modulus, then the area must be halved. So this should be a half A. So this should be a half, so that when I multiply a half times 2, I go back to the original expression there. So which single change gives an extension of 2x? So half the cross-sectional area of the wire, that is very correct. When the cross-sectional area is a half, it means the extension is 2x, so that the Young modulus remains the same. So the answer is going to be, it can't be half the diameter, because remember, area is directly proportional to diameter squared. So the answer is going to be A. Which force extension graph shows plastic deformation? Plastic deformation. This is elastic, that is elastic. So the answer is going to be D. When the deforming force is removed, the material retains some extension. So that is plastic deformation. Four solid steel rods, each of length 2 meters and cross-sectional area 250 millimeters squared, equally support an object 10 kilonewtons. They equally support. The weight of the object causes the rods to contract by 0.1 millimeter. So we have answered such a question. Let's see the contraction of one rod if it was used alone. Since there are 4, it's like they're in parallel. So if they all contract by 0.1, if it was alone, then it should be 0.1 times 4. So contraction of one rod would be equal to 0.1 times 4, which is going to be 0.4 millimeters. So to find Young modulus of that rod, I will say force over cross-sectional area times the original length over extension. So the force is going to be, if it was alone, to be 10,000. Original length is 2 meters divided by the cross-sectional area, which is 250, times 10 power negative 6 to change it to meters squared. Then the extension of one rod would be 0.4 times 10 power negative 3. When I press my calculator, I have 20,000 divided by 250 exponent negative 6 and 0.4 exponent negative 3, which is giving me 2 times 10 power 11, which means the answer is going to be B. The graph shown was plotted in an experiment on a metal wire. The shaded area represents the total strain energy stored in stretching the wire. So we know that strain energy can be a half Fx. So the shaded area represents total strain energy stored in stretching the wire. How should the axes be labeled? Remember, the strain energy is always area with the extension axis. That means the x-axis should be extension. So the answer is going to be A. The variation with applied force of the extension of a spring is shown in the graph. When there is no force applied to the string, it has length 1 centimeter. When there is no force, what is the increase in the strain energy stored in the spring when its length is increased from 2 centimeters to 3 centimeters? So let's see. At 2 centimeters, the extension is going to be 2 minus original length, which is 1. The extension is 1 centimeter. Then at 3 centimeters, the extension will be 3 minus the original length, which is going to be 2 centimeters. So the extension changes from 1 centimeter to 2 centimeters. The extension changes from 1 centimeter to 2 centimeters. So we need this area here. The increase in strain energy is going to be equal to a half. We are taking it as a trapezium, so that will be 2 plus 4. Then times the difference in extension, which is 2 minus 1, that will be 1 times 10 power negative 2. So this is going to be equal to 6 over 2, which is 3 times 10 power, that is 3 times 10 power negative 2, which is 0.03 joules. So the answer is B. Note very carefully that I couldn't use 2 centimeters and 3 centimeters because these are length. The examiner makes the word length bold. And this is a graph of extension. So I needed to first find the extension. At 2 centimeters, when the length is 2 centimeters, the extension is 2 minus original length. When the length is 3 centimeters, the extension is 3 minus original length. So it means the extension changes from 1 centimeter to 2 centimeters. To determine the Young modulus of a wire, several measurements are taken. In which law can the measurements not be taken directly with the stated apparatus? Let's check. Area of cross-section of wire, micrometer screw gauge. We can't measure the area directly with the micrometer screw gauge. The micrometer screw gauge will only give us diameter, so the answer is going to be A. Extension, vernier scale, that one is fine. Mass, electronic balance, fine. Original length, meter rule, that's fine. A long thin metal wire is suspended from a fixed support and hangs vertically. Masses are suspended from its lower end. The load on the wire on the lower end is increased from 0 and then decreased back to 0. The diagram shows the force extension graph produced. Where on the graph would the elastic limit be found? Where on the graph would the elastic limit be found? Of course, the elastic limit would only be found here because when you go beyond this, the material retains some extension when the deforming force is removed. So it means it will be exactly at point S. No, not exact at point S. It could be just beyond point S. Because point S could be the proportionality limit. So just beyond point S. Just beyond, slightly beyond point S. I said exactly point S, this is the proportionality limit. Limit of proportionality. Okay, proportionality limit or limit of proportionality. The diagram represents a steel tube with a wall thickness W, which is small in comparison with the diameter of the tube. The tube is under tension caused by a force T parallel to the axis of the tube. To reduce the stress in the material of the tube, it is proposed to thicken the wall. The tube diameter and the tension being constant, which wall thickness gives half the stress. So we know that stress is equal to force over cross-sectional area, and we know that the cross-sectional area is going to be directly proportional to the thickness. Cross-sectional area is going to be directly proportional to thickness. Stress is inversely proportional to area. Therefore, stress will be inversely proportional to the thickness of the material. So since the stress has been halved, it means the thickness should be doubled. So if stress is doubled and stress is inversely proportional to thickness, then stress is halved. Stress is halved. If stress is halved, then W is doubled because they're inversely proportional. So the answer is going to be C. And lastly, for part 2, I will stop on this page. The graph shows the nonlinear force extension curve for a wire made from a new composite material. What could be the value of the strain energy stored in the wire when it is stretched elastically to point P? So I will just get two areas. The strain energy should be greater than a half times the base, which is 2 times 10 power negative 3 to change it to meters, times the height, which is 100. So the strain energy should be greater than this value, 0.5 times 2 exponent negative 3, then times 100. The strain energy should be greater than 0.1 joules. That means this one is wrong and this one is wrong. But the strain energy should be less than area of a rectangle, that is going to be 2 times 10 power negative 3, then times 100 for the rectangle. So 2 exponent negative 3, then times 100, which is 0.2. So it should be less than 0.2 joules. So this one is also wrong. Why? Because 0.2 joules involves this part here where the curve is not. It should be greater than 0.1 because there is this space here which the triangle leaves out. So our answer is going to be C. The diagram shows the stress-strain graph for bone. What is the Young modulus of bone? So Young modulus is going to be stress divided by strain. So I'll just take up to 2. I'll just simply say 2 times 10 power 6 divided by the strain is given as a percentage. So this is going to be 1%, which is 1 over 100. So this is going to give us 2 times 10 power 8 because the 100 goes up. So our answer is going to be D. And lastly, a non-tensile force acts on a wire. The wire does not exceed the elastic limit, its elastic limit. Which two measurements enable the strain of the wire to be calculated? Remember, strain is equal to extension over original length. Okay, the unstretched length of the wire and the cross-sectional area. That one does not give us the strain. The unstretched length of the wire and the extension, that is strain. So the answer is going to be B. Okay, that marks the end of part 2, and see you in part 3. Bye bye.